Hello friends, welcome to the channel. Last video we discussed about molar conductance and its variation with dilution. In this video we are going to study a few more terms in electrochemistry. Come on, let's get started. We saw that on infinite dilution all the electrolytes are completely dissociated. Okay, but we could see that the molar conductance of one electrolyte and other electrolyte vary. Okay, if you take the two electrolytes like KCl and NaCl, okay, both the electrolytes on infinite dilution are completely dissociated to Ka plus and Cl minus ions and NaCl and Cl minus ion. Yet you could see the molar conductance of KCl at infinite dilution is greater when compared to the molar conductance of NaCl at infinite dilution. So why this change? Okay, why the KCl has higher molar conductance when compared to NaCl at infinite concentration? The reason for this is ionic mobility. Okay, ionic mobility. Ionic mobility is nothing but the speed of the ion. Okay, ionic mobility is given by denoted by letter mu. Okay, ionic mobility is denoted by the letter U and it is given by the formula U is equal to, that is ionic mobility is equal to speed of the ion by potential gradient applied. Okay, speed of ion divided by potential gradient. Okay, we all know speed is distance traveled by the ion divided by time in seconds. Okay, so ionic mobility is speed by potential gradient, in which speed is equal to distance traveled by the ion divided by time in seconds. Okay, and what is potential gradient? Potential gradient is potential difference applied, right? The potential difference we applied at the electrodes divided by the distance between two electrodes. Okay, distance between the electrodes. Okay, so ionic mobility is given by speed of the ion by potential gradient. So speed in turn is given by distance traveled by the ion by the time taken in seconds, and potential gradient is given by potential difference applied between the ions divided by distance between the ions. Okay, so in case of NaCl and KCl, we said KCl is having higher molar conductance than NaCl. We'll see why. Okay, here both Cl and Cl minus are common ions in both, so there'd be only difference in the speed of K plus and Na plus ions. Okay, Na plus ion is comparatively smaller than potassium plus ions, right? So for ions, the smaller ions like lithium plus and Na plus, we see that the speed of the ion, that is mobility of ion, is very less. Why so? This is due to hydration. Okay, hydration of ions. Okay, the Na plus ions and Cl minus ions, due to their small size and higher charge density, are heavily hydrated when compared to larger ions like K plus, etc. Okay, now due to hydration, if suppose it's Na plus ion and it is surrounded by water molecules, okay, that is solvent molecules, water. So when it is other solvent, it is called as solvation. When it is water, it is called as hydration. So it is hydrated, that is water molecules are surrounded over the Na plus ion. So now if Na plus had to move towards its respective electrode, it has to carry the whole water molecules that is surrounded and move. So the speed of the ion decreases due to increase in the size of ion due to hydration. So now if you see the Na plus ion and K plus ion size, now Na plus ion size will be greater than that of K plus ion due to hydration. Hence mobility decreases due to increase in size. Okay, that's the reason why KCl has higher molar conductance when compared to NaCl. Okay, now we shall see the ionic mobility of H plus ion in water. Okay, H plus ion is the least ion. So now we take two ions, H plus and K plus ion in water, and we compare the ionic mobilities of H plus and K plus ion. Okay, if I ask you now which ion either H plus or K plus, which has the highest ionic mobility in water. Then you might say that K plus has a higher ionic mobility when compared to H plus, because K plus is a larger ion and H plus is a smaller ion, and being a smaller ion, it gets hydrated, and on hydration the size of H plus ion increases. Hence the ionic mobility of H plus ion decreases, and hence K plus ion has higher mobility than H plus ion. But it is not true. Okay, but it is not true. It is seen that H plus ion has 5 to 10 times higher ionic mobility than K plus. It is seen that H plus ion has 5 to 10 times higher ionic mobility than K plus. Why so? We all know H plus ion in water exists as H3O plus, right? Hydronium ion. So in water it is also like other molecules like sodium, lithium plus, being a small charge, it is also hydrated, and hydronium ion is particularly trihydrate, trihydrated, and exists as H3O plus dot 3H2O. The structure of this is, so this is the hydronium ion, right? So you know the this has hydrogen bond. This hydrogen forms hydrogen bonding with oxygen. Hence this is the structure of H plus ion in water. It exists as trihydrate of hydronium ion. So this structure can easily explain us the greater ionic mobility of H plus ions. This can be explained by a mechanism called Groth's type mechanism. Groth's type mechanism. We all know that hydrogen bond exists in water molecule. Hence this hydrogen atom in turn will be hydrogen bonded to the oxygen atom of the other water molecule. So there will be another water molecule and there will be a hydrogen bonding between them, and for this there will be another water molecule and there will be hydrogen bond between them, and so on, right? So what happens is this: the H plus ion from this water molecule will pass via the hydrogen bond to other water molecule. So the H plus ion will move from this water molecule to here, then from here, or from here to here, then from next molecule. So the H plus ion will be moving from one water molecule to other water molecule via the hydrogen bond. So though if you see the H plus ion is being trihydrated, yet the H plus ion is moving. That is, this is called as proton pump. It is moving from one molecule to another molecule via the hydrogen bonding. So there is ion. So the ionic mobility of H plus is higher when compared to K plus, because now the H plus ion size is very small, right? Because it's not moving along with the trihydrate. It is moving only as H plus ion from one molecule, one water molecule to another water molecule as via the hydrogen bonding, and hence it reaches its respective electrode. So being small size, and hence the molar mobility also will be more for H plus when compared to K plus. In fact, we can see that the ionic mobility of H plus ion is greater than all the other ions. It is also seen that the ionic mobility of H plus ion in water and ionic mobility of H plus ion in ice. Okay, if we compare this both, ionic mobility of H plus ion in water and ionic mobility of H plus ion in ice, we see that the ionic mobility is greater in ice than in water. Why so? Because in ice is a crystalline structure, hence the molecules are oriented properly and there is a arrangement, okay, orderly arrangement. Hence we could see that water molecules exist in tetrahedral and also they are properly oriented. Hence the hydrogen ion transfer by the hydrogen bond will be very easy when compared to water. Hence the mobility also will be more in ice than in water. Okay, now if we see the effect of temperature, okay, temperature, you see that as temperature increases, ionic mobility also increases. So ionic mobility generally increases with increase in temperature. That's all about ionic mobility. Okay, next we are going to discuss about transport number. Okay, the transport number of cation. If you see the transport number of cation, it is denoted by T plus, and transport number of anion as T minus. Okay, so the transport number can be written as U plus by U plus plus U minus. Okay, so here U is the ionic mobility and U plus indicates ionic mobility of cation and U minus indicates ionic mobility of anion. Okay, so transport number of cation is equal to ionic mobility of cation divided by the ionic mobility of cation plus ionic mobility of anion. Okay, similarly for T minus it would be like transport number of anion is ionic mobility of anion by the sum of both ionic mobilities. Okay, so if you see what is actually transport number means, so transport number is the fraction of charge carried by each ion. Okay, so transport number means the fraction of total current carried by each ion and is given by its relation with ionic mobility is T plus is equal to U plus by U plus plus U minus. Okay, also T plus plus T minus is equal to 1. Okay, so if we know the transport number of one other cation or anion, we can find the transport number of the other one. Okay, so T plus plus T minus is equal to 1. So experimentally, transport number can be determined by two methods. One is Hittorf's method and the other one is moving boundary method. Okay, by these two methods, transport number is experimentally determined. So now just now you saw the relation between transport number and ionic mobility. Similarly, we can see the relationship between transport number and molar conductance at infinite dilution. So the transport number, if we consider infinite dilution, is equal to molar conductance of cation at infinite dilution divided by molar conductance of the solution at infinite dilution, right? So lambda m naught is equal to lambda plus naught plus lambda minus naught. Okay, this is called Kohlraush law, which we'll study in few minutes. Okay, this is all about transport number. Okay, next topic we are going to discuss is Kohlraush law. So when we studied about the molar conductance of strong electrolytes, we said that by extrapolating the graph we can find the lambda m naught value, right? Lambda m naught value we could for strong electrolytes we could find by extrapolating the graph, but for weak electrolytes we can find by Kohlraush law, right? So the lambda m naught value, that is the molar conductance of infinite dilution for weak electrolytes, can be determined by Kohlraush law. Kohlraush law is given by lambda m naught is equal to lambda plus naught plus lambda minus naught. where lambda plus naught is the molar conductance of cation at infinite dilution, and this is molar conductance of anion at infinite dilution. So we can say that the molar conductance of the solution at infinite dilution is equal to the sum of molar conductance of cation and anion at infinite dilution. This is what is called as Kohlraush law. Okay, hence by knowing the molar conductance of these ions, we can find the molar conductance of the solution and at infinite dilution for particularly weak electrolytes. Okay, now let's see the application of Kohlraush law. So its main application is to find the molar conductance of infinite dilution of weak electrolytes. So how we are going to calculate it? Okay, so we know the weak electrolyte example is acetic acid, right? CH3COOH. Okay, so you want to find the molar conductance of acetic acid, right? So you are going to find the molar conductance of infinite dilution of acetic acid. So acetic acid is dissociated as, it is partially dissociated because it is a weak electrolyte. So it is going to be CH3COO minus ion plus H plus ion, right? So acetic acids get dissociated as CH3OH minus ion, acetate ion and H plus ion. Okay. So now we are going to find the values. Okay. Suppose we have the values of lambda m naught of CH3COO Na. Okay. Lambda naught value of HCl and lambda naught value of NaCl, because we are going to find, if you want to find the lambda naught value of CH3COH, we cannot find by experimental, we cannot find it because it is a weak electrolyte. So we are going to indirectly find it by Kohlraush law. But sodium acetate, HCl and NaCl are strong electrolytes, right? So it can be found experimentally by extrapolating the graph, right? So by using these values and applying this in Kohlraush law, we are going to find the lambda m naught value of acetic acid. Okay, so how we are going to do it, right? So lambda m naught of acetic acid can be get from this two, right? So you can get this, right? So lambda naught of, this is dissociated as CH3COO minus, okay, and this as Na plus, right? This as H plus lambda naught Cl minus. So we got this both. We need these two ions, right? H plus and CH3CON minus ion. These two are something, okay? These two are our something addition, right, for us. So we have to eliminate these two ions. So minus from NaCl is being dissociated as Na plus minus Cl minus. Okay. So we are going to calculate this acetic acid molar conductance using these three strong electrolytes. So this is being dissociated as CH3O minus Na plus, H plus Cl minus, and Na plus and Cl minus. Okay. So what happens now? This will be getting cancelled, and we can get this value, which in turn we can find the molar conductance of CH3COOH. Okay. Thank you for watching.